It's a pleasure to be here. Thank you very much, all the people that organized this. It's a pleasure to have worked on this together with Olivier Millet and François Nicot. And I'm going to talk about how you can describe deformation in granular materials at different scales. So this is a nice follow-up to what Bernard talked about just before. So granular materials consist of particles, and especially if you look at the microscale, you have particles, and what is important is the context between particles. And at the microscale, we more or less say we know the important quantities are, Cauchy stress and strain for the time being, and the object of such studies, micromechanical studies, is to investigate relationships between the microscale parameters and the macroscale parameters. So one aspect, if you have information from a discrete element method simulation indicated on the left, how do you go to the continuum level by a suitable homogenization procedure? Well, this picture I think Bernard showed very briefly, so this is a nice opportunity to acknowledge his impact on the scientific community, so I call this the Cambu scheme. How do you develop constitutive relations by going through the microscale? So in the end you are interested in the relation between stress and strain at the continuum level. How do we accomplish this? We make an assumption about how microscopic strain determines at the micro level particle displacements and rotations. We invoke the local constitutive relation at the microscale, we get forces, and by a suitable averaging scheme we go to the stress, average stress. So my talk will not be about this whole procedure, but about one aspect of this process. How do you average from information on particle displacements and rotation? How do you get the average displacement gradient? So granular materials are special materials in continuum mechanical sense that they have, besides translational degree of freedom, they have rotations. And that means that if you look at the deformation at the contact point, there will be a contribution due to translations, but there will also be a contributions to due to the rotations. So the question that I will try to answer here is, how can you formulate an expression for the average displacement gradient in terms of the displacements of the particles and, importantly, the rotations of the particle? And of course this will also involve local geometrical quantities. So what is some definitions? What is the average displacement gradient? Well, first the displacement gradient, we look at small strain, so that's ui is my displacement, and I take my displacement gradient is denoted by alpha. And generally we are not interested in a very local value, but we want to average it over a certain domain. So we just say our average, indicated by the square brackets, is the integral over some domain, and then we divide by the area of the domain. Well, this you can rewrite in terms of the average strain theorem using Gauss' theorem. So that means that the average strain is determined by the displacements completely determined by the displacement at the boundary as well as by the normal vector. Okay, so if we look back at that average strain relation, then we see that it satisfies a surface-additivity property. If I have a certain surface and I divide it into two surfaces, S1 on the left, S2 on the right, and I calculate the average over surface S1 and I calculate the average over surface S2, then it always should be that if I look at the average for the complete surface, it should be given by this surface additivity form, where area times the average over the whole is equal to the area of the part times the average over the part plus the same contribution for the same. So this will be an important aspect that we build into our relation for the average strain. So now come to the specific objective of this study, so to formulate a micromechanical relation for the average displacement gradient. We look at specifically contributions of translations as well as rotations, and we want to reformulate that expression in such a way that it is expressed in terms of relative displacements at contacts. And also we want to make sure that this surface additivity relation is satisfied by the ultimate result. And in order to accomplish this, we make our life simpler. We just restrict ourselves to the two-dimensional case where we can do the important steps without any problem. Okay, so the building block of this approach is looking at what was called the mesoscale by Bernard. So we have a network of particles indicated by the circles in this case, which is not essential. We have lines between particles that are in contact, and you can see, you cannot prove it mathematically, but this is a tessellation of the complete area. So that means we can divide the total surface into the loops. So if we now are able to determine a average displacement gradient over one loop as indicated here in red, and we do that for all the loops, then we can use our surface additivity property to get to the average strain of the whole system. Okay, so let's go back to the average strain theorem. So we have been able to reduce the problem to determining the average strain over one loop. So we have to, for the determination of the average strain over that loop, we have to integrate over the boundary of the loop the displacement at the boundary in the normal vector. So here we have a small loop, in this case consisting of 4 particles. Well, the boundary of this loop is well defined, so we can determine the normal vector here, that's not a problem. The point that needs some attention is how to define the displacement at the boundary of this loop. Well, we know that this boundary, here this part, this part, this part, it goes completely through the particles. Inside the particles, the displacement can be described as being a rigid body, because the displacement of the particles, the strain, the deformation of the particles is small. They behave almost as if they were rigid bodies. So that means that if you look at the boundary, we can use express the displacement there in terms of translations and rotations. So let's look at this part. First we look at the translation part. Well, if we look along this part, the translation part for this particle is constant, so we have this green displacement field due to the contribution due to translations. To look at the contribution of particle rotation, we look at this side, and just shown for a different side for visual clarity. Particles rotate, that means that they have a linear variation of the displacement due to translation along this boundary. And so if this particle moves counterclockwise, this gives us a displacement field as shown here by the red arrows. So that means that we are able to express the displacement along the boundary of this loop in terms of the displacement of the particles and their rotations. So we have managed to get an expression for the average displacement gradient for a single loop. Well, you can manipulate this a little bit further in order to get an expression in terms of relative displacements. This is the final result. So this is one loop. We get an expression for area times the average displacement gradient, and it consists over a sum over the sides, and we have one contribution that involves the displacements of the particles, and we have one contribution that involves the rotations of the particles. So let's look at the translation part. We have here a difference between the displacements of this particle and the previous particle, so that's a relative displacement. It also involves a geometrical vector, y here, that's from the center of the loop to the contact point. And if you look at the contribution, the second contribution due to particle rotations, we have here the omegas, the particle rotations, and we have here geometrical factors r, which are related to the position vector from the center to the contact point. So these are all local quantities that you can determine if you know this tessellation into the loops, into the mesoscale domains. Well, this is all formulation based on paper. Does this work? So we did an extensive verification of this expression. So we did DEM simulations, a biaxial test, imposed deformation in the vertical direction and constant stress in the lateral direction. For that case, we can determine the macro deformation from the deformation of the bounding walls, and we can use our expression that we developed to get the deformation from the microscale information. I did not show the results here because you just get lines that overlap, so we completely reproduce the macro deformation in terms of the micro deformation. Another case is a shear test. So we start with a square box, we shear it, we determine the solution from the DM simulation, we compare the micro deformation from the developed expression, we compare it to the microscopic deformation of the box, and again we find that the complete agreement between the macro and the micro deformation. So that completes the verification. The second example is the most difficult one because it involves an average rotation of the particles. Okay, so now that we are certain that our method works well, we are going to look at a more complex case. So we have a deformation with a shear band. So this is again DM simulation by Najib Hada. We have, this is the geometry. You have an imposed strain in the vertical direction, constant confining stress in the horizontal direction. And if we look at the shear strength, that's a plot on the left with imposed strain epsilon 1. We see an increase in the shear strength. The peak in shear strength is reached, and then we see a drop, softening, and then a constant shear strength. The volumetric strain, we have that's the second plot. So we have an initial compaction, and then we have dilatancy and a sort of constant deformation at almost constant volume. Okay, so we again can determine the deformation of the walls. That gives us the macroscopic deformation. We can use our micromechanical expression that gives us the micro deformation, and we're going to compare them again. So on the horizontal axis is imposed strain, on the vertical axis are the components of the displacement gradient, and we see here markers that are the micromechanical expression. Solid lines are the macroscopic deformation determined from the deformation of the box. We see here a line which is horizontal, which is an imposed one, that's reproduced completely. We have a lateral strain, that's this line, also reproduced completely. So the diagonal terms of the displacement gradient are completely recovered. Then we see initially of the diagonal terms they are 0, and after a certain strain, roughly 1%, we see that they are non-zero, while the value that we would expect from the deformation of the box, which does not involve any rotation, that should be 0. So initially it's 0, and then it starts to deviate. So we're going to try to investigate the origin of that deviation. So that's this plot. On the horizontal axis is the shear strength. On the vertical axis are the off-diagonal component of the average displacement gradient. Macroscopically, we expect that value to be 0, and we see initially it is 0, and we see that once the peak shear strength has been reached, the value no longer is 0. So that leads us to suggest that the arisal of this off-diagonal component is due to the shear band that forms after the point of peak shear strength is reached. Okay, so based on some visual interpretation of the results of the simulation, this is the complete domain. We have divided it into 3 parts. Part A is the bottom, part C is the top, and part B in between is a region where we suspect that a shear band is visible based on plots of the displacements. Our expression for the deformation allows us to identify different parts, different domains, and we can determine the average displacement, average deformation in each of the 3 parts. So now we're going to compare them. So on the top left we have the 1,1 component. We see we have here the green is C and the blue is A. So these are parts, the top and the bottom part, they have small deformation, while we see that the red crosses, those are part B, so the major deformation is inside the shear band. And then we skip a little bit to the 2,2 component. We see the same pattern. We see that the part A, the bottom and the top, they have small deformation, while the major part of the deformation is localized in this, what we assume to be the shear band. Then the off-diagonal components, well, the off-diagonal components are 0 for the part A and the part C, but the off-diagonal components only arise in the shear band. So what we see from this picture is 2 points. We have the bottom part A and the top part C. They behave more or less as rigid bodies. Deformation is localized in part B, and if you look at the displacement along the boundary of the assembly, you see the displacement as it is shown here. So at the boundary there is a displacement that not only is outwards but also upwards. So if you use Gauss' theorem, that tells you that the granular system inside the box, it develops due to the contribution of this displacement along the boundary, a off-diagonal term. So the walls cannot completely impose the deformation on the granular system. Okay, so you can also look at the deformation in detail. So for each loop you can compute the average displacement gradient. You can make colorful plots like this one, where the color represents a scaled volumetric strain. So you see that this is the shear band, so that's where the deformation is localized. Again, the part at the bottom is more or less behaving as a rigid body, and the top again also behaves like a rigid body, but you see that there are patches of deformation outside of the shear band. So by the part that I will not show, you can make profiles of deformation over the shear band. If you do that, then you find that the shear band is quite a bit thicker than you would expect from visual observations. Okay, so then I come to my conclusions. We have developed a micromechanical expression for the average displacement gradients. It is a formulation that accounts for both particle translations as well as particle rotations. It is formulated in such a manner that it involves relative displacements between particles that are in contact, and importantly it is constructed in such a way that it satisfies this surface-additivity property. We have performed an extensive verification of the biaxial test and of the simple shear test to see that this expression reproduces deformation at the boundary, which it does. So we were confident that we could use this formulation to study the deformation in a complex case with a shear band. Then the important conclusion, we added the contribution of particle rotations to the average displacement gradient, but if you quantify their contribution to the average displacement gradient, then their contribution is negligible. So even in the case where you have very localized deformation, particle rotations do not significantly contribute to the average displacement gradient. They do, however, contribute to the average rotation, and that is still work that is still going on. So, I hope I am on time. I would like to thank you for your attention, and if you want to know more information, this is the reference from the paper. Now I'm upset, yeah. This is a provocation.
You want to joke?
No, no, it's okay.
I want to know, even at using mass weighted expression for your averaging formulas, and just use displacement might be quite tricky in the sense that displacement are not additive over values, while linear momentum and angular momentum are additive over values. So why didn't you weight your expression by the masses? Particles in your by the mass, by the volume?
I do it by volume, that's what you...
And what is it on your...
Yeah, so this is my expression for the average strain, and I want to make sure that if I have a continuous, if I divide this into two parts, and my displacement is continuous over this interface that I choose, then it should be, I can write it for the part on the left, I can write it for the part on the right, and if the displacement is continuous at the middle, then that part of the boundary just cancels out. So this is the logical way to do it. That is always, so in the end, the result that you get, it's always consistent with the displacements at the boundary, because those are the only ones that contribute to the average strain. And if you look at quasi-static deformation, the mass is not really relevant, I think.
I'm not very comfortable with the term micromechanical approach, because for me micromechanics, I give you the phases and the behavior of each phase, the behavior between each phase, and you give me the results. But here, you have to incorporate all the displacements inside the local loop, okay? Can we say that in fact you have proved that the local loop is a convenient RDE to average all the kinematic and static quantities for the macroscopic behavior?
Yeah, so what I use is very detailed information in order to verify the expression. You can also write it in terms of suitable averages. The other right side is full. So maybe if you look at the expression for the stress, which is pretty similar, you can write it as a sum over all contacts of contact forces and branch factors. This is a Love-Weber relation. You can also, instead of having discrete sum, which would suggest that you need all the information at all the contacts, you can write this as a integral over some average contact force that depends on the orientation. And the same for the branch factor. The theta times some contact distribution function. So ultimately it is more expedient not to write this at the contact level, but introduce suitable average where you say, okay, if I have contacts with more or less the same orientation, they share very many commonalities in their behavior. And so in the end, you use this expression as a checking your results, and also to get ideas of how to get this arrow down, how to develop that assumption. So what I showed here is actually only this red arrow.